Hello again everyone, welcome back to ptet.chemistry channel. So this is a tutorial video on preparing stock solutions as well as the associated dilutions. These are concepts that are related to what we have covered under solutions chemistry for the year 9 O level or IGCSE level for the 14 to 16 years old chemistry learners all around the world. Okay, so before I start, if you know what I'm doing on my channel, so there's a lot of chemistry tutorial videos suitable for 14 to 18 years old students, whether they're doing the O level, the IGCSE, the A level, the IB chemistry syllabus, or whatever syllabus they're doing all around the world. So don't forget to click the button on the bottom right to subscribe to the channel to get notifications and all the latest updates on tutorial videos, of which are abundant on my channel. And yeah, there should be something for everyone on my channel. Okay, so don't forget to get connected as well on Instagram, Facebook, and Twitter at ptet.chemistry. That is ptet.chemistry. Send in your messages, send your questions, and yeah, I look forward to hearing from you. Okay, let's get started. So what we have here is we're trying to make our stock solution. That's the direct thing that I'm trying to say. So these are all questions on how to prepare a standard solution. You started from the solid. So KMnO4 is a giant ionic structure solid because it's got, whoops, what am I doing? It's got K plus, it's got MnO4 minus. So what we're saying is it's an ionic compound, which means it's got giant ionic structure, which is something you know in year 9. And that's a result of it. You got ionic bond, you got strong ionic bond between the cation and the anion. Okay. So what we have here is we have the solid and we're trying to make up the solution. So your mole is the same because everything in the solid goes into the solution. So your mole is going to be the same. You are just adding water. Just add water. Water meaning distilled water in this context. You do not add the KMnO4. You do not lose the KMnO4. All of the solid goes into the solution. And you're trying to make how much volume? 1.0 dm cube. And you're trying to make 0.0300 mole per dm cube solution. This is dm minus 3. If you think about 10 to the minus 3, it means 1 over 10 to the 3. So dm minus 3 means 1 over dm3. So that means per dm cube, per dm cube. It's all just mathematics. Anyway, so we know the mole of the solid KMnO4 is equal to the mole of the KMnO4 solution. For the solid, we have the mass of KMnO4. That is what we are asked to find. Then given this information, I really should be working out the MR of KMnO4, which is going to be 39.1 times 1 plus the Mn, which is 454.9 times 1. What am I doing? 39.1 plus 54.9 times 1. I get 94 on my calculator, but I know because these are given to one decimal place, I should be getting 94.0 plus 16.0 times 1. My calculator show me 110. By right, I should really have it to 110.0 because of the accuracy of these relative atomic masses being given to one decimal place, unlike the usual one that you are given in your periodic table for O level or IGCSE level chemistry. These questions specifically give you these things because they're looking for specific accuracy. Anyway, just saying that, these are decision making. In terms of the mole of the solution, I have volume, I have concentration because I've dissolved it in water. How many mole of the substance dissolve in 1 dm cube of water? That is the definition. That is the meaning of meaning of solution. It's a mixture. You're dissolving it in 1 dm cube of distilled water. So what you have is concentration times volume. Concentration is in mole per dm cube, and this is already in dm cube. So here is one of these instances where I do not have to divide by 1,000 because I can follow the units. Physicists, mathematicians, well now chemists, you can follow the units. Okay, so I want the mass of KMnO4, so you will move up the 110.0, meaning to say they will just multiply. Before I press my calculator, I will always express myself very, very clearly first. Then when the time comes, I just need to press my calculator and I get 3.3 gram. However, if you read the question carefully, using a 2 decimal place mass balance, okay, I'm pretty sure you might miss that if you didn't read carefully. this thing is a 1 decimal place. You want to prepare using a 2 decimal place mass balance. So the mass that you're going to get from a 2 decimal place balance will not be 1 decimal place. It will be 3.30. That's what your calculator show you, 3.3, but your brain needs to think a little bit better to decide better. Now describe how you can accurately prepare this standard solution. You already weigh out the mass. So what is the next thing you would do? You would transfer the solid, weigh out the solid weigh, meaning the 3.30 gram of the solid, into a 250 cm3 beaker. And then you add distilled water. You want to add distilled water and not just water, because distilled water contains no dissolved ions. It's a pure H2O to dissolve the solid. You don't want that much distilled water, so give or take around 100 cm3 should be alright. Remember that you are making out to 1 dm3, so if you use 100 cm3, you are not going to exceed 1000 cm3. Okay, transfer, then you add distilled water to dissolve the solid. Transfer the solution, because now the solid already dissolved in the distilled water. Transfer the solution into a, not just any volumetric flask, but specifically you want to make it up to 1.0 dm3. So you want a 1.0 dm3 volumetric flask. And then what is very important is you must wash your beaker. What I mean wash is not just with tap water, but wash it with more distilled water, because you might have a little bit of that solid left in there. Give or take, if we use 50 cm3, 2 or 3 times separately. So you want to wash them not all in at one go, but separately. But each time when you wash, you combine the washing. Each time combining the washings into the volumetric flask, into the same volumetric flask. So these instructions, you do not ever have to memorize them, because you have done this in the lab with me. You might have seen me doing it. You can catch out my experimental tutorial video on making our stock solution. If you haven't done it before ever in your entire life, then you really must know at least one time how to do it. Then the next time you're just recalling your experience, it's just like writing a diary of what you had done and what you would do the next time you're presented with a scenario. So you combine the washing in the same volumetric flask. Then what you do is add more distilled water. So you want to just top up, add more distilled water until we reach, add more distilled water until we reach 250.0 cm3 mark. Do drop wise towards the end, or add drop wise, because you want to do it drop by drop. Okay, add drop wise towards the end. Okay, so I am getting to the end of the line here. So what do we need to do here? After we add it up to 250.0 cm3, do not forget to shake. You must shake, and this is the most important thing. If you don't shake it, you don't get the same concentration throughout. Shake to mix well. It goes without saying that you obviously need to stopper the flask before you shake it. That's why I didn't mention stopper, because without the stopper, the whole thing is just gonna fall apart onto the ground if you try to invert it without the stopper. So it goes without saying that there's a given. All right, so shake to mix well, and you have gotten your solution. On to the next part of the question. Why in the world did you not prepare this concentration? So just now you were preparing up to 0.0300. So to get 0.0300 mole per dm3, we need how much we need just now? We need 3.30 gram. So 3.30 gram of that KMnO4. Therefore, if you want to get even smaller concentration, so I'm just thinking about dilution because it's the same substance. Therefore, we need 3.30 divided by how many times? From here to here, how much smaller does it get? So you can do 3.0 times 10 to the minus 4 divided by 0.03. So that is about 100 times smaller. So I can do 3.30 gram divided by 100, and I would need 0.033 gram needed. Remember just now your mass balance can measure only up to 2 decimal place. If I look at this, my mass balance is not going to do very well. Your mass balance only 2 decimal place mass balance. So if I want this very small concentration, then I would need only 0.033 gram needed. Okay, so if we prepare, I don't like the word we, to prepare that small concentration, meaning the times 10 to the minus 4, that small concentration. So I should probably clarify 3.0 times 10 to the minus 4 mole per dm cube. I've shown the calculation. We need only 0.033 gram of solid KMNO form. Not accurate enough to weigh that particular mass. On the 2 decimal place mass balance. Based on the instruction given, you only have a 2 decimal place mass balance. So it's better to prepare these from a 3.30 gram, which is measured accurately using a 2 decimal place mass balance. And then you can dilute it 100 times. Dilution, just add water. Dilute 100 times. Okay. To the next question. So we have what looks like a very complicated one, but these are concentration of Ki, these are concentration of this sodium thiosulfate. So you have Na plus, you have 2 of them, so it's S2 or 3,2 minus. This is a very important ion. Well, it will get very important sometime in a couple of months or sometime early next year. This is called thiosulfate ion. You also have access to this thing H2O2. You have seen H2O2 in your practical on gas collection. This is called hydrogen peroxide. So these are all vocabulary that you should have gotten accustomed to based on what we have done in the classroom. H2SO4 is sulfuric acid, and you have a suitable indicator for this reaction. You don't use methyl orange because this is not an acid-base reaction, by the way. In any case, this is about the same idea. From the solid, you're going to prepare 250 cm cube of the solution. So these are the solid. The question is how much of the solid you need. So the mole of the solid is going to be the same as the mole of the solution. You have 250.0 cm cube. So I need to convert that to dm cube. To convert that to dm cube, I divide by 1000. The concentration of solution A that's needed is 0.100. 0.100. I don't know the mass of the solid, so the mass of the Ki, probably best if I do M and then bracket Ki. I need the MR of the Ki, so I can do this on the side. Based on the information given, the MR of the Ki is 39.1 plus 126.9. I get 166.0. Your calculator will not show you the 0.0. That one is decision making again based on the 1 decimal place AR as given in the question. So there's 166.0. So the mass of Ki, well, you can bring up the 166.0. It's going to be multiplied by this whole thing because of the the underlying mathematics, which is very difficult for me to explain because it's all mathematics, and primarily there's something you have done in primary school, lower secondary, and these kind of skills that bringing it up to upper secondary. Remember here, if you read the question carefully, the mass balance measure up to 2 decimal place. Now the student weigh the empty weighing board. So you have a container that you use to weigh the solid. Then you add the solid Ki to the weighing board until the mass was reached. Transfer all of the Ki from the board into the beaker. How? Describe. How can you check that the mass transfer is exactly the same as the mass calculated in 1? You wanted it to be 4.15 gram of solid added. So what you can do is you can weigh the beaker, weigh the 100 cm cube beaker, tare, T-A-R-E, is the same as 0. There's a button T or press 0 on the mass balance. That will mean that it takes away the mass of the beaker, and then add in the solid, add in the solid from the weighing board. That should read 4.15 gram as required. You want 4.15 gram to goes into the beaker, right? So you want to make sure that it's exactly the same as what you calculated that goes into the beaker. So you weigh the mass of the empty beaker, you make it 0, put in all the solid, then that mass on the mass balance after you put in all the solid should read 4.15, provided that nothing is stuck on the weighing board, everything goes into the beaker. Okay, on to the next one. This is basically making up the stock solution again. We are using distilled water, not tap water, because tap water contains dissolved ions. It's a mixture. And then you want to describe how the student should transfer all the Ki solution from the beaker into the volumetric flask, and how the student should fill the volumetric flask up to the 250 cm³ mark. This is the most important one. You have to talk about the dropwise towards the end, but you don't do dropwise from the very beginning. Okay, first of all, how the student should transfer. Well, now that you already got it dissolved in a 100 cm³ beaker in distilled water, so pour the solution in the beaker into the volumetric flask. But you don't just pour once, you need to then wash the beaker with a small volume or small amount of distilled water 2 or 3 times. And then each time, these are separately, by the way, so you want to wash it 2 or 3 times separately. Should really improve my handwriting a little bit. 2 or 3 times separately, each time combining washing into the volumetric flask, combining washings into volumetric flask. Okay, I think I've written quite long enough. How should you fill up the volumetric flask up to 250 cm³ mark? Then add distilled water until very close to the 250 cm³ mark. But that is when you slow down, you no longer pour. Then use a dropper, or you can say use a dropping pipette. So not a pipette, but a dropping pipette, okay, to add distilled water dropwise. Drop by drop mean dropwise until the 250.0 cm³ mark. And that's it. Okay, so on to the next one. So before we use a burette, so typically you will rinse with water because you don't know, distilled water because you don't know what was the last thing that the person used. But after you rinse it with water, there might be some water left in the burette. Any amount of distilled water left in the burette can contaminate. Sorry, not just contaminate, they can dilute, they can change the concentration of your solution that you are filling it in, and therefore it's important to get the right stuff in your burette before you actually use it, so to get rid of all the water that might be used for washing. Why this improve the accuracy of the results? Because rinsing with solution A will get rid or will remove any distilled water or other contaminants that can dilute concentration of A. Therefore, changes volume of titer. So by doing this rinsing with A, you avoid it because you will get rid of these thing in the burette, or other contaminants, I should say, in the burette. And these things can cause a different titer, because once your concentration of your solution in the burette get a little bit diluted, then they can affect your final endpoint there. Finally, this is about dilution here. So what we have is we are given 0.400 mole per dm cube. So the dm minus 3 there means per dm cube. So this is per dm cube. And what do I want? I want to prepare solution B. What was solution B? Let's read again. Solution B was 0.0500. So I want 0.0500 mole per dm cube. So this is dilution. Dilution means start from the concentrated and then add up the water to this. How much solution do I want here? I want 100 cm3 of B, so 100.0 cm3 of B. Fairly accurate stuff. You look at the precision, no way I should be using measuring cylinder. Okay, so I don't know the volume of this concentrate stuff. I'm just adding water, so the mole is the same, but of course the volume is not the same. It's like when you have a syrup, you add some water and then you get a diluted drink. So the mole is the same, so 0.400 mole per dm cube times the volume of the concentrated solution. If this is in cm cube, let me say this thing is in cm cube as well. If I say it is in cm cube, then I have to divide it by 1000, because mole per dm cube times the volume in dm cube is equal to the mole here. So the mole, there's concentration, mole per dm cube, times the volume in mole per dm cube. So what I get then in the end is volume concentrate. Move your numbers around first before pressing your calculator. It's one of the biggest danger that people can do. Use bracket definitely. Okay, you might not like this very well. Then I have all this thing on the right hand side. I move up the 1000 to the top, so it's multiplied by 1000. And then I move down the 0.400 to the bottom, so it's 1000 divided by 0.400. As you can imagine, it's 0.400 over 1000 times this, so it's this thing divided by 0.400 over 1000, so it's multiplied by 1000 over 0.400. That is your primary school division. Okay, use bracket very carefully and be able to do this kind of rearrangement very well. If you can do math, then you can do physics, then you can do chemistry. Unfortunately, if you can't do math, if you can't do physics that well, then your chemistry is going to struggle. We got to also know how to read as well. So give your answer to 2 decimal place. This is 1 decimal place as shown on your calculator. So be very careful about this kind of little things. Little things are what defines someone who is just good and someone who can be great. Next question. So we have potassium manganate 7. So you have seen this in the alternative to practical paper, K plus and MnO4 minus. This is manganate 7. This is purple in color. You want to determine the amount of iron present. But here you have the mass. You have the mass of this solid, and you are making up to 250.0 cm cube of this 0.200 mole per dm cube solution. The mole is the same because all the solid go into the solution. So the mole of the solid is equal to the mole of the solution. If I do mass over mR, but of course I don't know the mR, and that is something as an all-level student you would be able to do based on this information given. The precision is quite precise there, even though they're all 0.0. I must be careful when I work out the mR there. Okay, so dot 2 H2O means plus. There are 2 water molecules, so 2 times the mR of water. So you have 23 times 2, 23.0 times 2, sorry, plus 12.0 times 2, plus 16.0 times 4. I get 134 on my calculator, but I know there's actually 134.0. And then I have 2 times 16, 2 times 18.0, because 18.0 is the mR based on these for 1 water. I have 2 water. So 134.0 plus 2 times 18.0. Again, my calculator is giving me 170. It should be 170.0. So mass over MR on the left hand side give me the mole of the solid. The mole of the solution there is 250 cm cube. So 250 divided by 1000 multiplied by the concentration, which is 0.200. So just make the mass of that solid and you move up the 170.0. So this is divide, so move to the other side. It will be this whole thing multiplied by 170. Whatever you do not write down the times 170 straight away, because this is equal to this. If you put in the 170.0, this shouldn't be there anymore. So a lot of students, well, actually not a lot of students, I've seen a couple of students who, they do their calculations like that, and their math is just not making any sense at all. If you see a calculator, they give you 8.5, and this is not sensible given the fact that you are looking at 1, 2, 3, and 4 sig fig, 1, 2, and 3 sig fig, and these are pretty accurate as well. And your mass balance as a result of these should reflect the accuracy. So I'll say to 2 decimal place, or you can say to 3 significant figure. Whichever way you look at it, it's going to reflect greater accuracy because you want to make something which is pretty accurate, especially the concentration is accurate to 3 significant figure. So I should probably say up to 3 significant figure rather than 2 decimal place there. Anyway, moving on. So you want to accurately prepare this solution. So you got to talk about the names and the capacities. So you already have the weighed sample, so you already have the solid. So transfer the solid that has been weighed out into a 250 cm cube beaker. So after that, you add maybe around 100 cm cube of distilled water. So got to be distilled water. As I mentioned previously, distilled water doesn't contain dissolved ions. So this is to dissolve the solid. After you dissolve the solid, you get a solution. So you transfer or you pour the solution into the volumetric flask. But be careful, you need to mention the names, you need to mention the capacities. You want to prepare 250.0 cm cube, so into a 250.0 cm cube volumetric flask. And to that, you need to wash the beaker a few times, so 2 or 3 times typically, with small volume of distilled water. This is to just dissolve out whatever solid that might still remain inside the beaker. And each time you have to combine the washing, each time combining whatever you wash the beaker with, combining washings into the same volumetric flask. I'm running out of space already for this 2-mark question. Anyway, add more distilled water until you reach the add more distilled water until the 250.0 cm cube mark. You should do it dropwise, or add dropwise when close. Okay, when close to the 250 cm cube mark. When close, I'm really running out of space. More importantly, you must shake it in order to mix well, because if you don't shake it, you are never going to get a standard stock solution. Okay. Anyway, so moving on to the last part, which is just calculations. So we are given this equation, 2 of that and 5 of that, because that's what we need. We also need the concentration of the KMnO4. So I have the mole of the MnO4 minus. These are ions, so do not ever just write down MnO4 on its own. These are ions. So maintain a good habit of writing down as you see the information. Okay. So the mole of MnO4 minus from the balance equation is 2. The mole of C2O42 minus from the balance equation is 5. So that is from the balance equation. And then on the other side, as I always express this way, will be the actual mole. The actual mole of C2O42 minus is going to be at the bottom because I've labeled this thing at the bottom. So it's 25.0 over 1000 because that's in cm cube multiplied by concentration mole per dm cube times volume in dm cube, because I divide 1000 will give me the actual mole of the C2O42 minus. On top, I will have the volume in cm cube converted to dm cube multiplied by the concentration of the MnO4 minus. So just need to make the concentration of MnO4 minus the subject of formula. So I'm going to bring up the whole thing. So this whole thing, better to bring it out as a bracket. So you're going to get 2 over 5 times 25.0 over 1000 times 0.200. I should probably have a bigger bracket. Now I can divide this whole thing by 18.40 over 1000. Okay, so I move up this whole thing and then I move this down, so it's called cross multiply, and I can get this as subject formula. You gotta be more comfortable with rearranging stuff and finding your unknown. This is just a little bit of algebra. It's not the most complicated thing in the world, but it does take practice, without which you are not going to get any better. So do the top bit, do the top bit first and then divide it by the bottom bit. So 18.40 times 10 to the minus 3, or you can do 18.40 divided by 1000. This is what my calculator show me, and this is ridiculous. I must have made a mistake somewhere. Let me check again. That seems like a huge concentration there. 2 over 5 times 25 over 1000 times 0.2. I get 2 times 10 to the minus 3 on top, divided by 18.40. Okay, this makes more sense. Now, well, I mean, after having done this kind of thing a lot of times, 96, and they want your answer to 3 significant figure. So 1, 2, and 3. So I look at the fourth one, and I can get 0.109 mole per dm cube. If you don't like this format, you can use mole per dm cube. But yeah, 3 significant figure. So 0.109 as our final answer there. I feel more comfortable bringing this up a little bit so that the space doesn't look so tight down there. But anyway, so that's the end of this tutorial video, which is basically on making stock solutions. We've done quite a lot of these things, from the solid to the solution, and then from the solution we can dilute it further. You've seen that this kind of mole calculation, setting up the mole ratio, doing solution chemistry involve a little bit of math and rearranging questions and getting things right when pressing your calculator. I hope it has been useful. If it has been, so browse around the channel for other useful tutorial videos. Do click the button on the bottom right, subscribe to the channel, and share the channel widely with friends, chat group, juniors, seniors, relatives, teachers, whoever else you think the channel might be useful for. And yeah, follow me at ptet.chemistry. That is ptet.chemistry on Instagram, Facebook, and Twitter to get connected, send in your messages and stuff. And yeah, thank you for watching. I'll see you in the next tutorial video.